There is a spacecraft that NASA intentionally threw into Jupiter. On September 21st, 2003, the Galileo spacecraft was guided into Jupiter's atmosphere, where it was destroyed within seconds. This was not a failure. Galileo had cost $1.39 billion, operated for nearly 14 years, and returned some of the most important data we have about Jupiter. And when its mission was complete, NASA destroyed it on purpose. Because allowing Galileo to remain carried a risk NASA was unwilling to accept, a risk created by Jupiter itself. And that same risk is why NASA does not attempt to go deeper into Jupiter. The data coming back from the probe didn't make sense. Scientists had sent the probe into Jupiter expecting to find a wet, turbulent atmosphere rich with water vapor and active storms. Instead, the probe descended into one of the driest, calmest regions anyone could have predicted. The atmosphere was hot, much hotter than models suggested, and the winds were faster. The probe measured wind speeds exceeding 600 kilometers per hour, and those winds didn't decrease with depth the way scientists expected. They stayed strong, even as the probe fell 150 kilometers below the cloud tops. But the biggest shock was the water, or rather, the lack of it. Jupiter should be rich in water. The planet formed beyond the frost line, the region of the early solar system where temperatures were cold enough for water to freeze into ice. As Jupiter grew, it should have swept up enormous amounts of water ice, along with everything else. The probe found water vapor, but not much, far less than expected. At the time, this was baffling. How could Jupiter be so dry? It took years to figure out what had happened. The probe had, by pure chance, descended into a hotspot. Hotspots are regions in Jupiter's atmosphere where the cloud deck has breaks, allowing thermal radiation from deep inside the planet to escape. They're rare, covering only a small fraction of Jupiter's surface. They're also exceptionally dry, because descending air in these regions suppresses cloud formation. The probe had essentially landed in Jupiter's version of a desert. It would be like sending a probe to Earth, having it land in the Sahara, and concluding that Earth is a dry planet. But even as scientists worked to understand the probe's data, Galileo itself was beginning its real mission, orbiting Jupiter and studying it from every angle. And what it found was stranger than anyone imagined. Jupiter doesn't just have an atmosphere. It has an atmosphere that extends thousands of kilometers deep, with no clear boundary between gas and liquid. As you descend into Jupiter, the pressure increases. At the cloud tops, where the probe entered, the pressure is about 1 bar, roughly equal to Earth's atmospheric pressure at sea level. Go deeper, and the pressure climbs rapidly. At about 1,000 kilometers down, the pressure reaches about 200,000 bars. That's 200,000 times the atmospheric pressure on Earth. At this depth, hydrogen stops behaving like a gas and starts behaving like a liquid. But it's not ordinary liquid hydrogen. Under these extreme pressures and temperatures, hydrogen enters a state that doesn't exist naturally anywhere on Earth. The electrons are stripped away from the hydrogen atoms, and the hydrogen becomes electrically conductive. It behaves like a metal. This is called liquid metallic hydrogen, and it makes up most of Jupiter's interior. Somewhere between 75 and 90% of the planet's mass exists in this state. The temperature at this depth is estimated to be around 10,000 degrees Celsius. The pressure is millions of times greater than anything we can create in a laboratory. And the metallic hydrogen is churning, convecting, driven by heat escaping from Jupiter's core. This convection, combined with Jupiter's rapid rotation, generates Jupiter's magnetic field. And that magnetic field is extraordinary. Jupiter's magnetic field is the strongest of any planet in the solar system. It's about 20,000 times stronger than Earth's. At Jupiter's equator, the magnetic field strength is roughly 4.3 Gauss. At the poles, it reaches 14 Gauss. For comparison, Earth's magnetic field at the surface is about 0.5 Gauss. This powerful field extends far into space, creating a magnetosphere that dwarfs anything in the solar system except the sun's. Jupiter's magnetosphere stretches 7 million kilometers toward the Sun and extends more than 600 million kilometers in the opposite direction, reaching all the way to Saturn's orbit. Inside this magnetosphere, charged particles are accelerated to nearly the speed of light. The radiation is intense enough to destroy spacecraft electronics in hours. Galileo was designed with heavy radiation shielding, but even so, the mission planners knew the spacecraft had a limited lifespan in Jupiter's radiation environment. And deep below all of this, hidden beneath thousands of kilometers of hydrogen, lies Jupiter's core. Or, at least, that's what scientists thought. For decades, planetary scientists assumed Jupiter had a dense, compact core at its center. Models suggested this core was made of rock and ice, with a mass somewhere between 10 and 20 times Earth's mass. This made sense. In the core accretion model of planet formation, Jupiter would have started as a rocky seed that grew large enough to gravitationally capture gas from the surrounding solar nebula. The core came first, the gas came later, but then Juno arrived. NASA's Juno spacecraft entered orbit around Jupiter on July 4, 2016. Its mission was to study Jupiter's interior by making precise measurements of the planet's gravitational field. Gravity isn't uniform. If a planet has a dense core, its gravitational pull will be slightly stronger over that core. By measuring tiny variations in gravity as Juno orbited Jupiter, scientists could map the distribution of mass inside the planet. The data Juno returned was shocking. Jupiter's core isn't compact. It's not a solid ball sitting at the center of the planet. Instead, it's diffuse, spread out, occupying up to half of Jupiter's radius. The core appears to be a mixture of heavy elements, gradually blending into the metallic hydrogen above it. There's no sharp boundary, no clear division, just a gradual transition from dense material to lighter material over thousands of kilometers. This was not what anyone predicted. Scientists scrambled to explain it. One theory suggested that Jupiter was hit by a massive object early in its history, something 10 or more times Earth's mass, colliding with Jupiter and mixing its core with the surrounding gas envelope. Computer simulations supported this idea. A head-on collision with a large planetary body could have shattered Jupiter's core and created the fuzzy, dilute structure Juno observed. But other simulations contradicted this. When researchers modeled giant impacts in detail, they found that even a violent collision wouldn't permanently mix the core material with the gas. Over time, the heavy elements would settle back down, reforming a compact core. The fuzzy core should be temporary, but Jupiter's core has been fuzzy for billions of years. A newer theory suggests the fuzzy core formed gradually during Jupiter's growth, as the planet accreted material in a chaotic, uneven process. This would explain why Saturn also appears to have a fuzzy core. Two fuzzy cores in two giant planets suggests a common formation process, not a random collision. But the truth is, we don't know. We don't know how Jupiter's core formed. We don't know if it's stable or slowly dissolving. We don't know how it connects to the metallic hydrogen above it or how it influences Jupiter's magnetic field. What we do know is that going deeper into Jupiter gets harder and more dangerous the farther you go. Jupiter kills spacecraft. This isn't an exaggeration. The radiation environment around Jupiter is lethal to electronics. Charged particles trapped in Jupiter's magnetosphere bombard anything that gets close, causing cumulative damage that eventually leads to failure. Galileo was built to survive this. The spacecraft carried heavy shielding around its most sensitive components. Its computer systems used radiation-hardened processors. Every circuit board, every wire, every sensor was designed with Jupiter's radiation in mind. Even so, Galileo barely lasted. Over the course of its mission, Galileo completed 34 orbits around Jupiter. Each orbit took it through different parts of the magnetosphere, exposing it to varying levels of radiation. The cumulative dose was staggering. By the end of the mission, Galileo had absorbed radiation equivalent to 60 million dental X-rays. That's enough to kill a human thousands of times over. The spacecraft's cameras failed. Several instruments stopped working. The onboard computer experienced memory errors. Juno faces the same challenge. The spacecraft's orbit was carefully designed to minimize radiation exposure. But even so, Juno is slowly dying. Two of its instruments, the infrared auroral mapper and the camera, were expected to fail by the 8th orbit. The microwave radiometer was designed to last through orbit 11. As of now, Juno has completed 37 orbits and is still operational, but the clock is ticking. The deeper you go into Jupiter, the worse it gets. The strongest radiation is concentrated in a belt that loops around Jupiter's equator, between the planet and its innermost moons. This is where charged particles from Io's volcanoes are ionized and accelerated to near-light speeds. Any probe attempting to descend deeper into Jupiter would have to pass through this belt. The radiation would be intense enough to fry electronics in minutes. But radiation isn't the only problem. The Galileo atmospheric probe survived for 57 minutes before it was destroyed. The cause of its failure wasn't the heat. It wasn't the winds. It was the pressure. When the probe's signal stopped, it was 150 kilometers below the cloud tops at a pressure of about 23 atmospheres. That's 23 times the pressure at Earth's surface, enough to crush the probe's transmitter. And the probe was still in the upper atmosphere. It hadn't even reached the region where hydrogen transitions from gas to liquid. If you wanted to send a probe deeper, to study the liquid hydrogen ocean or the metallic hydrogen layer or the core, you would need a vessel capable of withstanding pressures millions of times greater than what the Galileo probe experienced. No such vessel exists. The deepest anyone has ever sent a probe on Earth is about 11 kilometers, to the bottom of the Mariana Trench. The pressure there is about 1,100 atmospheres. The vessels that go there are small, spherical, made of titanium, and they can't carry much in the way of instruments. To reach the depths of Jupiter, you would need something far more robust, a probe capable of surviving pressures exceeding 1 million atmospheres, temperatures of tens of thousands of degrees, radiation that would destroy any known material in seconds. And even if you could build such a probe, how would it transmit data? Radio waves don't penetrate liquid metallic hydrogen. Any signal from deep inside Jupiter would be blocked by thousands of kilometers of electrically conductive material. You would need a relay system, multiple probes at different depths, each passing data upward to the next, until finally a signal could escape to a waiting orbiter. The engineering challenges are immense. The costs would be astronomical. And for what? To answer questions about Jupiter's interior that may not even be answerable with our current technology. NASA has considered it. So have other space agencies. But every time, the conclusion is the same. Going deeper into Jupiter is, right now, impossible. There's another reason NASA is cautious about Jupiter. It's not just about the planet itself. It's about what orbits it. Jupiter has 97 known moons. Most of them are small, irregular chunks of rock and ice captured from the asteroid belt or the Kuiper belt. But 4 of them are different. Io, Europa, Ganymede, and Callisto. The Galilean moons, named after Galileo Galilei, who discovered them in 1610. These moons are worlds in their own right. Ganymede is larger than the planet Mercury. Europa and Callisto are roughly the size of Earth's moon. All 4 orbit within Jupiter's magnetosphere, protected from the solar wind but bombarded by radiation from Jupiter itself. Io is the most volcanically active body in the solar system. Its surface is covered with active volcanoes, erupting constantly, spewing sulfur and sulfur dioxide into space. This material forms a torus around Jupiter, a donut-shaped ring of ionized gas that feeds Jupiter's magnetosphere. Europa is different. Its surface is ice, smooth and cracked, crisscrossed with lines and ridges that suggest the ice is floating on something liquid below. That something is water. Europa almost certainly has a subsurface ocean, a global ocean of liquid water sandwiched between the icy crust and a rocky core. The ocean is kept warm by tidal heating, the same process that drives Io's volcanoes. As Europa orbits Jupiter, the planet's gravity stretches and compresses the moon, generating friction and heat. This ocean could be 100 kilometers deep. It could contain more water than all of Earth's oceans combined, and it could harbor life. This is why NASA destroyed Galileo. By 2003, Galileo was dying. Its propellant was nearly gone, its systems were failing, the spacecraft was going to crash into Jupiter eventually, and NASA had no way to prevent it. But if Galileo crashed uncontrolled, there was a chance it could hit Europa. A small chance, but not zero. And if Galileo hit Europa, it could contaminate the Moon's ocean with microbes from Earth, bacteria that survived the journey through space and might survive the impact. NASA couldn't allow that risk, so they made the decision to steer Galileo into Jupiter deliberately, ensuring it would burn up in the atmosphere rather than risk contaminating Europa. The same reasoning applies to any future mission. Any spacecraft that goes to Jupiter must be sterilized or destroyed before it poses a contamination risk to Europa or any other potentially habitable moon. This adds another layer of complexity to any mission that would attempt to go deep into Jupiter. Not only would the mission have to survive Jupiter's radiation and pressure, it would also have to be designed in a way that ensures it won't contaminate any of Jupiter's moons when it inevitably fails. In 2017, Juno flew directly over the Great Red Spot. The spacecraft's instruments peered deep into the storm, using microwave wavelengths to penetrate the clouds and measure what lay beneath. What they found was remarkable. The Great Red Spot isn't just a surface feature. It extends deep into Jupiter's atmosphere, reaching down more than 350 kilometers below the cloud tops. At that depth, the storm encounters the region where water is expected to condense, and yet it continues even deeper. The storm is also changing. Observations from Earth show that the Great Red Spot has been shrinking for more than a century. In the late 1800s, it was about 41,000 kilometers across. Today, it's roughly 16,500 kilometers wide. It's losing about 930 kilometers per year. No one knows why. Some models suggest the storm is stable, that it will persist indefinitely as long as Jupiter's atmospheric conditions remain the same. Other models suggest it's slowly dissipating, that it might disappear within a few decades. If the Great Red Spot does disappear, it would be a significant loss. The storm has been a constant feature of Jupiter for as long as we've been observing the planet. Losing it would be like losing a landmark, a reference point that's been there for centuries. But there are other storms on Jupiter. Smaller storms, cyclones, and anticyclones scattered across the planet's surface. Juno discovered something strange about these storms. At Jupiter's poles, the storms form geometric patterns. 9 cyclones in the north, arranged in an octagonal pattern around a central storm. 5 in the south, forming a pentagon. These storms are enormous, each one larger than the entire United States. They rotate at speeds exceeding 300 kilometers per hour. And they're stable. They don't merge. They don't dissipate. They just sit there, locked in place, for years. No one knows why they form these patterns. No one knows why they're stable. Computer models can't replicate them. The physics that govern these storms are still poorly understood. And these are just the storms we can see from orbit. What lies deeper, in the regions Juno's instruments can't reach, remains a mystery. NASA isn't done with Jupiter. Neither is ESA or any of the other space agencies planning missions to the outer solar system. The European Space Agency's Jupiter Icy Moon Explorer, or JUICE, launched on April 14, 2023. The spacecraft is currently on its way to Jupiter, scheduled to arrive in 2031. Its mission is to study Ganymede, Callisto, and Europa, with a focus on understanding their potential habitability. NASA's Europa Clipper launched on October 14, 2024. It will arrive at Jupiter in 2030 and conduct dozens of flybys of Europa, studying the Moon's ice shell, subsurface ocean, and surface composition in unprecedented detail. Both missions will spend years in the Jovian system, returning data that will help us understand not just Jupiter, but the entire class of gas giant planets. But neither mission will go deep into Jupiter itself. That remains, for now, beyond our reach. The challenges are too great. The radiation is too intense. The pressures are too extreme. And the scientific questions we could answer by going deeper may not justify the enormous cost and risk of such a mission. But that doesn't mean we've given up. Engineers are working on new materials that can withstand higher radiation doses. New designs for atmospheric probes that could survive deeper descents. New propulsion systems that could slow a probe's fall and extend its operational lifetime. Some researchers have proposed using a nuclear-powered probe, one that could generate its own electricity even in the depths of Jupiter's atmosphere, where solar panels would be useless. Others have suggested a swarm of smaller probes, each descending to a different depth, creating a network of sensors that could map Jupiter's interior in 3 dimensions. These are ideas. Nothing has been built. Nothing has been funded. But the conversations are happening. And as our technology improves, as our understanding of Jupiter deepens, the possibility of going deeper becomes a little less impossible. So why is NASA scared to go deeper into Jupiter? Scared isn't quite the right word. Cautious might be better. Respectful. Jupiter is a hostile environment. It's a place where spacecraft die quickly, where probes are crushed and vaporized, where radiation tears apart electronics at the atomic level. Going deeper into Jupiter means accepting that any mission will be short-lived, that the data returned will be limited, that the cost will be high and the risks immense. But it's more than that. Going deeper into Jupiter means confronting the limits of our technology and our understanding. It means asking questions we may not be able to answer. It means venturing into a realm so extreme, so unlike anything we've encountered, that we can't predict what we'll find. And there's always the risk of contamination. Any mission to Jupiter must be designed with the moons in mind. Europa, Ganymede, Callisto. These are places where life might exist. Protecting them is paramount. NASA isn't scared of Jupiter. But they understand what Jupiter is. They understand the challenges. And they understand that some mysteries take time to solve. For now, we watch from orbit. We study Jupiter's clouds, its storms, its magnetic field. We measure its gravity and map its interior from a distance. We send our spacecraft as close as we dare, gathering data, pushing the limits of what's possible. And slowly, piece by piece, we're learning what Jupiter is and how it came to be. Jupiter was the first planet to form in our solar system. It shaped the orbits of the other planets. It protected Earth from countless asteroid impacts. It carved gaps in the protoplanetary disk and influenced the formation of the terrestrial planets. Without Jupiter, Earth might not exist. Or if it did, it might look very different. Understanding Jupiter means understanding our own origins. It means understanding how solar systems form and evolve. It means understanding the forces that created the world we live on. And there's so much we still don't know. We don't know exactly how Jupiter's core formed or why it's fuzzy. We don't know what drives the storms at its poles or why the great red spot is shrinking. We don't know how deep the winds extend or what lies at the very center of the planet. We don't know if there's a solid surface somewhere deep inside or if it's liquid all the way down. We don't know how the metallic hydrogen behaves or how it generates Jupiter's magnetic field. Every answer we get leads to new questions. Every mission reveals new mysteries. And that's how science works. Jupiter isn't just a planet, it's a laboratory. A place where we can test our theories about physics, chemistry, planetary formation, and the limits of what's possible. Going deeper into Jupiter isn't just about satisfying curiosity. It's about pushing the boundaries of human knowledge. It's about learning what we don't know and figuring out how to find the answers. Someday, we'll build a probe that can go deeper. Someday, we'll develop the technology to survive Jupiter's depths and return data from regions no instrument has ever reached. But for now, we're still learning, still observing, still asking questions. And Jupiter, massive and mysterious, continues to spin in the darkness, keeping its secrets close.